Welcome everybody. Leonardo, great to meet you.
Great to meet you too.
I'm Peter, I run the rest of the project. Super fantastic to have you here. Also want to just welcome Michael Whitbrook as well. Some of you know Michael from early interactions. He's from New Zealand, visiting for a day. He'll be around to find out what we're doing. He also has an interest in research assistance. Some people are talking with you, Leonardo, this afternoon, and also we have a slot 2:30 to 3:30 this afternoon where I'm just going to do a round table with Michael. Completely optional if anyone wants to come in here, what Michael and his group are up to and share what they're up to. Please come along. That'll be in Shannon at 2:30. And I think that's it. Is there anything else anybody else wants to add? Just saying congratulations to people pushing out ARR papers yesterday. There was a lot of frantic emails. Well, today, that's right. 4 a.m. today, we were pushing papers out, so that's awesome. Yeah. All right, that's it. I'll pass it over to you.
Okay, great. So very happy to have Leonardo here. I'm happy that you wrote your title here because it's a rather long one. So Senior Principal Applied Scientist at Amazon. Prior to this, he was for many years at Microsoft Research. So leading figure in the automated reasoning community, worked on everything from SAT to SMT to theorem proving, more broadly, decision problems. He's the author of, for example, the Z3 solver, which I know people here are familiar with, as well as the lean solver, which is what he'll be talking about today. And the lean solver has been used increasingly by mathematicians for doing things like verifying mathematics. And I think the lean community is a bit unique in that they've been also embracing generative AI technology. So I invited him to talk about that. And yeah, so feel free to take over.
Thank you.
We usually have questions in between, if that's okay for you.
Yeah, yes, please stop me. Happy to answer questions during the talk. And yeah, I want to give you a small introduction about Lean and applications. I mean, how people are building AI on top of Lean for mathematics. Feel free to interrupt me. Super happy to be here. Right. Lean ranges the domain of formal methods, right, where you specify, design, and verify complex systems with mathematical rigor. Right. I can show an example what we mean by specification. For example, suppose that we're trying to implement a function that computes maximum of 2 natural numbers. We can write the spec, right? The spec says that the result should be greater than or equal to the inputs, right? And should be one of them, right? And you have the design, the actual implementation, and you have the verification that shows that your implementation meets the specification. And in Lean, you can do all that. You can specify, you can implement, and you can verify that your implementation meets the specification. Lean is also used for mathematics, right? But the main thing, the main idea, I think, that's why many people in AI is interested in Lean, is because the formal proofs are machine checkable proofs, right? There are many people trying to build AI that create proofs automatically, right? Using large language models, but these systems hallucinate. They have tiny mistakes. Sometimes it's really tricky to get the mistake, where the mistake is. But if you, instead of synthesizing formal proofs, you synthesize formal ones, you can use Lean to check these proofs. Right. Another thing that is important to keep in mind: proofs are not in a vacuum, right? When you build a proof in mathematics, especially in cutting-edge mathematics, you're on top of you need lots of results that you have been formalized before. You need a huge library, and Lean has a big library, right? It's growing very rapidly. Is hitting 1.5 million lines of code now, the Lean mathematical library, and is growing, right? And one of our goals in the Lean Focused Research Organization is to accelerate the progress. But let's see a small example of a proof, right? Here's a proof for every single A, B, and C natural numbers. If A equals B and C equals B, then A equals C, right? It's a very simple proof, but the main point here that you have these terms that are the actual proofs, right? Basically, I'm showing you have transitivity, you have symmetry, and that's how the proof is being constructed. And this can be checked. Lean will give you absolute confidence whether the proof is correct or not. Machine checkable proofs are relevant for AI, but one thing the math community was really excited about, and you're going to see many examples of that, they also enable people to collaborate. People that never met each other can collaborate. Right. For example, with Terence Tao is the greatest living mathematician today. He was blown away that his project, 30 people helped him formalizing the proof, people that he never met before, people filling gaps, and he didn't have to check. The computer was checking the proofs are correct or not.
Can I ask a question about that previous slide?
Okay.
So there's a very strong associativity property, right? It's like there are parentheses on the right-hand side of the first implication. Is it like good lean syntax to not put in parentheses? Right. So A equals B implies C equals B implies A equals C, right?
Yes.
So that seems like syntactically opaque a little bit.
Well, it's not clear to you what the precedence is.
Exactly. I had to think for a while to work out the precedence, and then I wondered, is it good practice not to put it in parentheses or whatever? Or you can't
Well, I think we use the standard precedences, the precedence levels that people use in mathematics, but people are free to put. And another thing that's to keep in mind that everything you can interact with these objects. And the computer will tell you the precedence. If you hover over these objects, it's going to tell you exactly what the precedence is, how to input these symbols. Sometimes there are implicit information on these terms that is being hidden from the user, and the computer will tell you, look, this is the implicit information that's hidden here. It's going to tell you the types. Is an interactive system. You can hover and one way the mathematicians put it is like you can zoom in at any level of detail you want, right?
One question. This might be the wrong time in the talk, but before I'm completely lost.
Yes.
Well, it's still simple enough. I understand what's on the screen. When you say there's a lot of theorems, already in Lean,
Yes.
do they typically come with like a natural language counterpart that kind of tells you what this theorem is saying?
It's great. We are going to get, there's a project called Lean Blueprints that mathematicians are embracing. That's the idea is that you create it's like literate programming where you combine informal with formal, right? And sometimes the leader of the project will set up everything, like the architecture of the proof. But the proofs, there are many holes to be filled. And then the community comes and fill the holes. And in the end, you have a website where you have the formal and informal next to each other. I will show an example.
Okay, great.
Like the same, you mentioned there's like lots and lots of previously proved things in the library. What's the granularity of that? Like what kind of lemmas or such are available? Are these big films? Are they tiny things like this?
No. It's massive. I mean, one of the projects, for example, Liquid Tensor project was Peter Schoz's. He's a Fields medalist. He got a Fields medal in 2016. And he said, my most important result I'm unsure about, and they verified using Lean. And it's cutting edge mathematics. Of course, Lean is not covering everything, right? It's like people say, there are things that are well developed, like number theory is really well developed, the library. Probability is getting much better. Analysis is getting better, but there are gaps, right? But some areas, you go to the level of PhD level, Fields medal level mathematics.
Related to that, is the coverage about the same as, say, whole step or something like that, or is it smaller or larger?
Oh, excuse me?
The whole step, the corpus of formally verified proofs, is the coverage inside that library about similar to coverage in whole step, or larger or smaller? Or?
It's larger. It's larger today. I think Lean by far today is the biggest mathematical library, right? And it's keep growing, and it will grow even faster now with attention, like with Turnstile giving talks now about Lean, saying he's attracting even more mathematicians to the community. But we claim that machine checkable proofs address the trust bottleneck between humans, because you don't need to trust someone to use their proofs because the system is checking the proof for you. But in the future, we also address the bottleneck between humans and machines. If the machines are synthesizing the proof, right? You take the proof, you don't need to check, even if it's incomprehensible, the computer is checking if the proof is correct or not for you. Lean basically, we had goals about being extensible. I think I will emphasize a lot. I think one of the successes, Lean is successful because it's an extensible system. We want it to be expressive. I mean, we want to be able to express cutting edge mathematics in the system. And scalability and efficiency are also really important, especially in software verification. We know software is complex, but in cutting edge mathematics, the complexity of the objects the mathematicians manipulate is dramatic. Right? If you zoom in all details, is so much information there. Right? The system, we have to invest a lot in scalability to be able to handle these objects. We view Lean as a platform for formalized mathematics, software development and verification, and for developing domain-specific languages, custom automation for that. Right? We strongly believe in the approach that was started with Haskell, where you could design your own domain-specific languages for particular problem domains. And the advantage of Lean is that you can design the language, but you can also reason about programs written in this language, right? You can prove properties about them. And we saw that as extra value. Lean has a small trusted kernel, right? What does that mean? Lean is a gigantic system, but the proof checker, right, the part you have to trust is much smaller, right? And everything, all the proofs are being checked by this small kernel. And we have external checkers. You can export your proofs. Your proofs are also another cool idea in machine checkable proofs is that proofs are data. You can export, you can analyze them, you can build graphs about them, and you can write your own external checker. And people do that.
Has the kernel been formally verified?
Not yet, not yet. We achieve, when people say, should I trust Lean? Our answer is you can implement your own checker. You can try to verify with all the checkers that exist today, but you can also write your own, right? And there are efforts to verify. There is one of the checkers written by the community was written in Lean itself. And in principle, you can verify this one, right? And there are people that are interested in doing that, but this is a major project, right? It's not something that will happen in the next few years, but will happen one day. Another way to do Lean is as an integrated development environment for formal methods, right? The math community using Lean is growing rapidly. They love the system. All your proofs and definitions are machine checkable. You can also view Lean as a compiler that goes from a high-level language to the kernel code that's checked by the kernel, right? I'm giving an example of Lean code here just to show that it looks like code, it looks like something like a program. And sometimes people view it as a weakness that looks like that, but is a strength at the same time, because all the goodies you have for programming, like jumping to definition, auto-completion, inspect the type of objects, all that is available, right? You can literally browse your development, keep jumping to definitions and inspecting at any level of detail you want. Even if you want to go back to the axioms of mathematics, you can. Here's an example showing that The previous example was showing that there are infinite primes. That is very basic, but you go to advanced mathematics, right? This is Stacks is a open source book, right? In Columbia, right? I mean, there are many results there, algebraic geometry and so on there. And many results from the Stacks library have been formalized in Lean.
The previous slide, so things like commutative ring and all that, these are objects defined or types
In the Lean
defined in
mathematical
Lean.
library, yes.
So that's what you fixed.
Yes. Correct. I mean, this part is really well developed in Lean. You have all these objects there.
Sorry for all these questions. What kind of coverage of the space of mathematics does Lean cover? Does like all areas of math or just some
Yes.
some aspects?
Yes, great question. For undergraduate mathematics, people track really carefully how much is more than 50% now, is like at 60%. So the coverage for undergraduate mathematics, for master's level, there's a lot. For PhD level, for some areas, as I said, people are doing cutting edge mathematics, but people estimate, today is 1.5 million. The math community estimates if everybody in the math world was using formal methods, the library would grow by 10 million lines per year to keep up with the math being developed every year, right? If everybody switches, that would be, I mean, it's a lot, right? 10 million lines per year, right?
Related to that question, is there a corpus taking the original source of, in normal mathematical notation, even images or anything, right, and associating with the Lean verifications of it? And if that exists, how good are language models at writing these things now? Yeah. Where's the leaderboard?
Yeah, we'll get there. I'll show how they do the mapping, how they map the informal world with the formal one. How the large language models are. Right now, we view opportunities for large language models that are in reach. Some things people claim, for example, if we talk with people from OpenAI, they say, oh, we're going to prove the Riemann hypothesis. I don't see this in the near future, right? I don't see any evidence. I mean, I'm going to show later an example, an embarrassing result, the proof, completely bogus proof the large language model creates for basic mathematical facts. So it's really far from that. But there's many things that are in reach for large language models. For example, assisting users learning the formal mathematics, helping users to find previously proven results, suggesting the next step, right? Not giving the full proof, but telling you, why don't you try this, right? This is in reach, right? There are many things that are in reach for large language models, right? I think this one we already talks about if we can trust Lean or not. I mean, we have external checkers. You can implement your own checker. Another idea in Lean is that we talked about machine checkable proofs, but another important topic in Lean is metaprogramming. Lean is implemented in Lean itself, right? And users can extend Lean using Lean. They can write their own proof automation. They can write their own visualization tool, their own custom notation, their own custom pretty printer. This graph here was generated using a program written by a mathematician, right? Basically, it's picking a result from the mathematical library and building the dependency graph, right? Showing many parts of the library, right, where the results are coming. And formal proofs, as I said, you don't need to trust me to use my proofs. You don't need to trust my proof automation to use it, right? You can hack without fear. And this allows users to create their own proof automation, even if it is buggy. If it works most of the time, people will use it, right? The kernel is checking the proof in the ends, right? If your proof automation is creating a proof that is accepted by the kernel, people will use it, right? The Lean mathematical library is managed. There are more than 300 contributors, And there's like a team of maintainers, like 30 people maintaining the library, right? The library is vast. I have some statistics here. The red line is the mathematical library for the latest version of Lean, that's called Lean 4. The blue one is for Lean 3, and MathLib 3 stopped. You see that's in the middle of next year, all development stopped in MathLib. And this rapid growth was people porting to Lean 4, right, the mathematical library. And after that, it keeps growing and is reaching almost 1.5 billion lines of code. There are more than 100,000 theorems there, more than 300 contributors to the library. And the library enables projects like many projects like the interfactoid spaces. Right? This project was the first one this project attracted many mathematicians to the Lean community. Kevin Buzzard, Johan, and Patrick, when they came they started playing with Lean, they felt like, wow, these other proof assistants, people formalizing results from the 70s. Right? This is cool, but mathematicians, they don't care. This is a dead area. Nobody's working in this area. If you want to attract mathematicians, you have to work in hot topics. And the factoid spaces, when they did it, was a hot topic. Peter Schulze had got a Fields Medal. He was the inventor of perfectoid spaces, and everybody was asking, what's a perfectoid space? And it's a complex mathematical object, right? Explaining in English what a perfectoid space, there's always some information lost in your explanation. And Kevin did the following. He formalizes in Lean, and in Method Overflow, he puts there, this is what it is, a perfectoid space. And now you can browse the developments, right? You can jump. If you don't know, for example, what a Tate ring is, you can just click and jump to the definition. Now you see what a Tate ring is, right? So it's interactive. Kevin was saying, this is like a 3D visualization software. If you have a geometrical object, you can understand it much better. If you see, if you can turn, you can zoom. Same thing here. If you have a formal version of the mathematical object, you can inspect it in many different ways. And this is because of this project, many mathematicians start coming to the Lean community. Today, we have these 4 different pillars, right? You have mathematics, where we have projects with Peter Schulze, with Terence Stahl, formal abstracts with Tom Hales, and many other projects. We have AI research. OpenAI built an assistant for Lean, Facebook AI. There's the IMO Grand Challenge, and so on. There are software developers now that use Lean for verified software, and it turns out a language that's great for writing proofs is also great for proving your programs, right? And I believe there's an impact on education, right? I meet all the time students that are great hackers, right? They learn to program by themselves, right? And they learn basically they got tutorials online, and they have a playground, a compiler or interpreter, right? And I met so many amazing kids, right? And for mathematics, this is rare. Usually, when you meet a kid that's is great in math, they had a great mentor. Someone saying, this is a good proof, this is good style, this is not good style. There's no place, if you don't have access to this mentor, right, a family member or a great school, it's really hard to become a good mathematician, right, with really rare exceptions. But we believe a proof assistant is the playground for you to learn mathematics, right? Sometimes we sit with a kid, they're a great hacker, say, I don't know what a proof is. You show Lean, they pick immediately, right? Now they can start hacking, they start writing their own proofs. Everything makes sense, right? Especially if the students learn to program in a functional programming language, right? Because then you tell them, oh, you know recursion? Yeah, induction is the same thing, right? Now you know how to do proofs by induction, right? And they get it immediately. The Lean nonprofits, one of the goals is to have impacts in education, right? We believe we will be able, today Lean, it was developed as a research prototype for many years. Now with the nonprofits, we want to transition of something that's polished, something that will be approachable to high school students. If you're playing with Lean, one place to visit is the Zulip chat. Right? The Zulip chat was another focal point. The community is where the community gathers, right? The mathematicians are there, AI people are there from OpenAI, from Meta, and so on. People from XAI, you find them there. You find fields medalists like Peter Schulze, Terence Stahl, he has an account there, he asks questions about Lean there. And you find students, right? Zulip is a great place to learn more about Lean. With that perfectoid space project, the next thing in 2020, the community starts growing a lot, and the mathematical library starts appearing like in popular science magazines like Wired, right? Then in 2021, we had this project, the liquid tensor experiment with Peter Schulze, where he had this new result he was unsure about. People were assuming the result was correct because he's a Fields medalist. And it turns out that people formalized the results and people simplified the proof. He was blown away that people simplify the proof without understanding the proof, right? Because now you have a computer there telling you if your steps are correct or not. You can try, you have some intuition, you can simplify something, and you make the modification, the computer accepts it, you keep going, right? So he was excited, not just because people verified, but because people simplified this proof, right? And this appears in Nature, this project. The head of the project, the formalization project, was Johan Kommelin. I strongly encourage anybody interested in formal mathematics to watch his talk about this project, Abstract Formalities, where he makes really good points about how mathematics can be done in the future, where you set the architecture of the project, you set clear abstraction boundaries, and you can parallelize the developments after that. It is a great talk. And after that, there are many other projects like these unit fractions. That's the results was formalized before it was refereed, right? Chingauer is a Fields medalist, and he was blown away that people verified the new results. This is an important result. There was an open problem that people proved it and verified in Lean before it was even refereed by in a math journal. Sphere inversion is another interesting project because people had doubts that a proof assistant could be used for geometric topology, right? They thought, oh, proof assistants work great for algebra, for number theory, but can we do geometric topology using a system like that? And turns out, yes, and they got new insights. Right. This project was the project that started the blueprint system, and I will talk more later. In 2023, Lean kept growing. It appears in the New York Times. Terence Stahl got excited about it. It appears in Quanta again. And we started having applications in cryptography. The Rust creator was praising Lean online. It was a great year for the project. But 2024 is looking promising too, right? A new result from Terence Stahl, he just not finished this proof with Chingauers and so on, but they also formalized it in Lean. He just gave a talk about machine-assisted proofs, right? How formal mathematics is important. DeepMind has formalized these results about AI safety using Lean. We have Lean copilots from NVIDIA and Caltech. Alex Kontorovich, Terence Stahl, they have a new project, Blueprint project. And I think now is a good time to show how Blueprints works. Right? It's like a literature programming. After you are done with Blueprints, he will generate a website for you. This is completely informal math, right? But here, what happens is that if you hover over the results, you see, oh, sorry, you get the link version. You can jump to the formal definition of this result. It is in a web browser. Everything can be searched there. And you can ask to see the source codes, and it shows you the formal version of this proof, right? I'm just showing a glimpse of the informal proof that there are. I put here, it continues the informal and the formal one, but they are side by side, and they were created using a single document, right? With a single document, you have the web version with the informal proof, with the formal one, and everything connects together.
When you say created, is it created by a person or by the machine or both together? Or
yeah, there's a tool. The informal version and the formal version are created by humans today, but there's a tool that automates the generation of the websites, the links, the hyperlinks, everything.
The formal version loaded in. I mean, you just give it a PDF and it takes it, or you have to like write all the typesetting commands again.
No, you don't. The generation. This is a website that's automatically generated.
I'm wondering the informal version.
Yeah.
How do you put that? Suppose you've got one. How do you get it in there in the first place?
Oh, you're going to put LaTeX embedded in your files. They're in LaTeX. I should have copies on the top. You'll see the LaTeX for this.
Okay, so you put in LaTeX.
Yes,
okay,
yes,
got it.
yeah. And there are groups also. I don't mention here, but there is a tool being developed called Lean Informal that converts formal proofs into informal ones. The idea is that you would write your, you don't have to write these anymore. You would get this and convert into an informal version that is readable by regular mathematicians that do not have formal training.
just to be clear, so Lean verifies proofs.
Yes.
Does it author proofs as well, or help?
Yes. Lean has a notion of a static language. I mean, you can view as actions. And the AI that's being built on top of Lean tries to guess these actions, these statics, right? And sometimes the actions are very simple, like this one is RW means rewrite. He writes with this term, apply this term as a rewriting rule. There are very small actions like that, but there are bigger actions like run, we have all these linear arithmetic facts. Run the decision procedure for linear arithmetic, right? Which is a procedure that's going to do many things, right?
So could Lean explore the space of possible proofs and see if they can find one, or is that?
Yes. For example, the meta, I will go to the meta. They have a tree search algorithm where they're exploring the space of proofs.
That's related to my question about whole step. Suppose you take that corpus and feed it into this automation, right? Completely unassisted. How often will it find a proof? I mean, and even if it was like 0.1%, that would be exciting, right?
Yes.
Has someone tried that on an existing corpus?
Yes, for simple things, there is a benchmark suite called Mini F2F.
Mini F2F?
Yeah. It's from OpenAI started this testing suite, but it's mostly their ambition is to get a gold. What the original ambition is, let's try to get a gold medal in International Mathematics Olympiads. Right, this is high school. This is really hard. I mean, it's high school mathematics, but it's really hard to get a gold medal there. But for advanced mathematics, as I said, I think it's in reach to guess the next step, suggest things, complete the proof is out of reach right now. But there are people actively working in this area. Extensibility is a big deal, right? We are building not for the community, but with the community. They are writing their own proof automation. They're extending Lean themselves. The ring tactic was written by the community, for example. And Lean is also efficient because people are writing, we wrote Lean, and people are writing the whole proof automation in Lean. Lean is also efficient programming language, right? And this is an exciting future for Lean. We believe in the future, people will be writing code that's running production, right? I mentioned before the talk, this project as Amazon Cedar, right, where they wrote the model for the Cedar language in Lean and proved many properties about this model, but it's not running in production, right? So in the future, this is going to become, this is where Lean is going, right? We envision a future where Lean is running production, where you verify properties about your programs and you have strong guarantees about their correctness. Lean is also support domain-specific languages, and in its implementation is everywhere, right? Lean has an extensible parser. It is important because mathematicians love to create their own notations. They're always creating new notations to try to compress information as much as possible. And this is a feature that we use to implement Lean itself, right? Lean is implemented in Lean, is used all over the place. I will try to get to the AI parts. I will skip the do notation and try to get to. Oh, let's talk a little bit about the Focus Research Organization, right? Last year, in August of last year, Lean we created a nonprofit for Lean called Lean FRO. FRO stands for Focus Research Organization. This is a concept that was created by Convergent Research. It's a new model for science. It's for projects that are too big for academia. There's no profitability path. A big corporation or a startup will not pursue. Is in the intersection of these three different areas of flow. You have funding. The idea is that you get funding for 5 years and you have to push your idea on these 5 years, right? And it started last August. We have 10 full-time employees now. There are 2 extra employees coming soon. And the Lean Flow is supported by the Simons Foundation, the Sloan Foundation, and Richard Murkin, right? The website is lean-flow.org, and we have a public roadmap, what is going to be done in these 5 years. And people say, but what you're doing there? We can summarize with this question that was posted in Zule. Well, MathLib is 1.5 million, but if you want to make it formal mathematics mainstream, it will be 100 times bigger, right? What do you do, right? How can you handle something massive? 100 times bigger is 150 million lines of code. This is bigger than Windows. This is bigger than Firefox, bigger than Rust, bigger than Linux. I mean, maybe bigger than all of them combined, right? How do you do that? How to scale, right? So scale is one of the big topics in the Lean Flow. Scalability is everywhere in mathematics. Like there was a hierarchy. You have so many concepts there, right? This picture here summarizes all the dependencies. You have so many concepts in math. Managing all these mathematical objects is a challenge, right? Automation is also a big deal. We want to reduce the overhead factor, right? Or the Bryan factor. The overhead factor is when you compare informal math with formal one. What's the overhead? How much bigger the formal version is? Today, for advanced math, is 20, right? 20 times bigger, right? Terence now only managed to finish his latest project because he got contributions from so many different people. If he had to do by himself, I probably would have given up, right? It's too much work. But we are working on automation, and AI will help, right? Usability is another big deal, right? These are integrated development environments. As I said, people interact with these objects, right? You can visualize, you click in your proof, you can visualize the proof state at that point. And this is not just a string, right? This is a live object. You can click and start seeing the internal data at any level of detail. People expect to have auto-completion, go to definition, and so on. More importantly, when something doesn't work, or when something works, the user wants to understand why it didn't work, why it worked. Being able to see interactive traces that show you what Lean did behind the scenes is extremely valuable to users, right? When they're trying to diagnose why a proof automation didn't work. And it goes beyond that. Users, since Lean is extensible, they can create their own visualizations. Here is just showing an example where the user defined a matte black tree, but they also described, they wrote a program that shows how to visualize the matte black tree. In the same file, they are visualizing, defining, and proving facts about red black trees. And now they can select terms and visualize them graphically. Right? People do that for category theory. For many different areas of mathematics, they're creating their own visualizations. And the language is another challenge. Nobody knows how full mathematics should look like, right? We are learning as we go. There's no spec, right? We're learning with the community. We get feedback from the community. Some things work well, some things do not work. And you have to keep adjusting and trying to create this language that would be great for doing formal mathematics. Engineering, there's a lot of engineering. It's not just research. There's lots and lots of engineering. Right? Building MathLib, people expect a cloud build system. There are mathematicians that do not have powerful computers to build MathLib in their notebook, but they want to get the latest version quickly. You want to get from the clouds a pre-compiled version. You want to have package managers, documentation generators, continuous integration, diagnostic tools. There are so many things that are needed to push a project like that. Now, let's spend the last 15 minutes talking about AI on top of Lean. Right? We know large language models are incredibly powerful, but they hallucinate. Here I have a simple question I asked the large language model to prove there are infinitely many integers between any two distinct integers, right? And it came up with a bogus proof for something that's not true. And it's not just GPT-4. I mean, you can try all available large language models, all the ones I could find, they all create various crazy proofs.
If you tell it to translate it into Lean, does it do a good job of it? And can you prove that it's false, that it's not valid? Yeah.
People are trying, some groups are trying to give better support for Lean. I will try to highlight some of the projects that are trying. Today, I mean, for GPT-4, he knows a little bit of Lean, but not that much.
And Gemini Ultra, how does it do? Have you tried?
Yeah, we try. Let's put like Tenstal put it. I mean, he learned Lean using large language models on the side. He said, well, most of the time is wrong. But even when it's wrong, it helped me to learn the syntax. He showed me, oh, that's what you it gave me a path. I think the large language models, the generic ones that were not customized for Lean, they are great for helping you learn, especially if you are learning Lean. He was side by side. I mean, the large language model on one screen, he kept asking questions, copying, pasting, and he found it valuable, right? And he documented everything on Mastodon. If you're interested on his insights, he has many cool insights about how the large language models helped him learn Lean. But you have projects like this one from OpenAI, GPT-F. This is not, it has nothing to do with GPT-4. It's a large language model trained for formal mathematics, right? And they managed to solve some IMO problems with this system, right? And sometimes it's really impressive, right? They came up here, the creativity, they came up with the auxiliary terms. The large language model invented P minus A, C minus B, C minus A. This is the creative step. After that, it fed these terms to action or attaching in Lean, and Lean finished the proof. The key part is coming up with the magical terms, and the large language model did it. This example, right? It's from IMO 1964. Meta actually managed to improve results. The results OpenAI has, right? And they have a hyper-tree proof search that's guided by a large language model. It's a much smaller model than GPT-4. I think around, if I'm not mistaken, around 100 million parameters. But they have engine like a program. They are trying to get inspiration from AlphaZero, where you have a tree search, and there's a large language model making suggestions, and they exploring the space. And they managed to solve also some IMO problems. The community felt, the mathematicians that tried, they provide an integration. Like you see it, that suggestions, they will suggest the next step. The professional mathematicians did not find it useful at this point. It's like you have to cross a bar. I mean, even if you mention 1% of the time, for them it was not good enough. I think it has to be much higher than that for them to pay attention to the suggestions, right? And for example, Lindojo today, this project from NVIDIA with Caltech, they even they test the suggestions before they put in green the ones that definitely work, but still, the professional mathematician doesn't feel like it's good. That you have to cross a bar for people to pay attention. Maybe what's being suggested there, they can do automatically. Another way a mathematician pointed out is that, yeah, these tools help. They finish some things, but they fail so many times. I have to learn to prove myself. After I learn to do it, yeah, I can do it. I mean, I don't need its help, right? I mean, there is a threshold that has to be crossed for these tools to be extremely valuable, especially for the power users. Another active area of research is auto-formalization. Like, Lean Chats is one of the many tools now. Lindojo has a version of that, but Lean Chats, what I think was the first one that allows you can write in English and you can have a dialogue with Lean Chat, and he'll give you the formal version of your statements, right? Allows you to convert informal mathematics to formal one, and you can ask it to make corrections if things do not work, and you interact. There's another one, Lean 8, that you can write. Sorry, the font is a little bit small. You can put in comments what you want, and it's going to show a light bulb. You click, and you convert into the formal version, right? This is also on GitHub, Lean 8. Lindojo is the one I mentioned before. Also, the cool thing about Lindojo is that the source code, the model, the data sets, everything is available online. Right? It's really important for people doing research to have everything, the whole pipeline, the open source, right? A GPTF project from OpenAI was not open source. Same thing for Meta. Lindojo, as far as I know, was the first one that they open source everything. If you go to their website, you can download the models, the data sets, everything. And there are many opportunities for combining AI with Lean, right? We have the machine checkable proofs, right? Auto-formalization will enable people to learn from mathematics, right? In the ideal world, it would be amazing where people interact in English, even if it's not fully precise, and you have AI converting to formal, And one thing we tell people is that reading is easier than writing, right? For example, we had one user that he told me, I learned to read Lean in one day. It took me weeks to learn to write, but reading is easy, right? And if you have an AI that can convert your prose into the formal version, would be valuable, right? You could interact in a completely different level, right? You would have the formal version and you can double check, yes, this is what I want, right? And it would enable you, having formal mathematics would be the first step to get something that is extremely valuable, that would be verified code synthesizers, right? Many people are excited about code synthesis using large language models, but having verified code synthesis is extremely valuable. Now, some tools that are relevant for that. I want to include these tools because trying to convince you to use Lean. And for example, one tool that is very popular with AI researchers is Lean REPL. Lean REPL allows you to control Lean using JSON messages. And there are AI groups now using it for doing reinforcement learning, for example. If you want to do alpha zero like architecture, you want to have probably your large language model infrastructure is all in Python, and you want to control Lean, you can use the Lean REPL for doing that. You can keep communicating with JSON messages to Lean REPL and completely control the system, right? Lean REPL is a super useful tool for AI researchers. Another one is Lean training data. It's a tool that allows you to traverse a Lean repository and create and extract training data for your large language models. I think this is a step on top of what Lean Dojo team has. It was built by Scott Morrison, that he's in the Lean nonprofits, and he's polishing this tool that is to provide tools to AI researchers in such a way they can extract data from the Lean, training data for large language models. For example, this tool will, for any point in the proof, is going to show, this is the proof state here. It's going to show you, at this point, that was the action that was took, and this is the new state. You're going to get the state before and after and the action, right? And people use this data for training large language models. And there's a lot of community excitement, right? I mean, for example, this user connected Lean to Houdini, that's a 3D visualization engine. He basically can define hybrid systems, right, in Lean and visualize them with this software, right? And everything is creates automatically. Because Lean is extensible, this is syntax, he created this syntax, right? Basically, you are defining, and you're saying, oh, show me this function. It generates a proof that this is smooth, it's Frenchable, and so on, right? He wrote all that by himself without having to talk to us, completely independent, in a completely decentralized way. Another application that mathematicians were really excited about is refactoring. I mean, in computer science, software projects, we have tools for refactoring our repositories automatically. But for mathematics, they just realized that. Right? And this mathematician was saying, wow, I can suppose that we generalize a result. Suppose this is a result that was published 50 years ago. I have a more general version. How do I propagate this change? Would have to go over all these papers in formal. Here, the system can do for you. Math is data now. You can propagate the changes automatically. And he was thrilled that this is possible now, right? You may put more work, make it formal, but because now everything is checked, everything, you can manipulate this data, you can propagate changes automatically, right? And he was thrilled when he figured out that the conclusion is like Lean is extensible to improver. You can learn more about Lean, leanprover.github.io. You can also, alias for this website is lean.lang.org. Lean supports decentralized collaboration. We strongly believe the MathLib community will change how mathematics is done and taught, right, in the future, right? In a way to summarize, that Peter Schulze says, it's not just about proving, right? It's about understanding complex objects. It's allowing you to go beyond your cognitive power, right? He said, I couldn't keep that proof for the liquid tensor. He says, I had trouble keeping all the objects in my head. Right? Having a computer there guiding me is valuable, right? Thank you very much.
Thank you. That was a wonderful overview of all the exciting things that are going on within your community. We're almost out of time, but are there any?
A quick question. So you had some systems that can try to take informal language and turn it into lean. Do you have things going the other way? Like here's a lean theorem, turn it into natural language, maybe at different levels of granularity?
Yes. This project, Lean Informal, is by Patrick Massot and Kyle Miller. They are developing a system. The main purpose of the system was education. It's like now you can convert a lean formal proof into an informal one that regular mathematicians without formal training could read and could benefit. And this informal proof had all these benefits of being able to click to jump to definition. Would be interactive documents that's written in prose style.
Because imagine if like a language model is trying to reason over a new problem and they want to access this database of earlier proofs.
Yes.
They have a natural language formulation and different granularities. It's easier to find them or think of them.
Yes.
This is how I think of theorems. I don't think of like all the details. I have some kind of abstraction of it in sort of higher level concepts.
All the AI researchers are excited about Lean Informal. I mean, if you go to Zulip, you're going to see them asking when Lean Informal is going to be ready, right? Because Lean Informal now will be like this Rosetta Stone. You can get, for every formal proof in MathLib, you'll be able to get an informal one. Now you have these pairs you can try to train the large language model showing. This is the formal version, right? Now you're creating a bridge between the formal and informal worlds. And people believe you're going to enable, the AI researchers believe, you're going to be able to do transfer learning. By learning into formal proofs, and you can generate variants of these proofs automatically behind the scenes by mutating the proofs and seeing if they still work. You can create tons of data. And many AI researchers believe this will enable large language models that are better at mathematics. They are going to be way better in mathematics by training with this extra data, right?
I had one question. They talked about the Lean community. How do you think, what's kind of a big problem that you think the AI or LLM community could help with that would help kind of Lean researchers or mathematicians?
Yes, I would love to see AI. Things that are in reach. Of course, there are things that are would be amazing, like, we have AI that can complete proofs automatically, right? It would be amazing to have that. But in the near future, having AI that helps people to learn to use the system, answer questions. When you're blocked, sometimes a user is blocked, what do? They go to Zulip, right, and ask a question there. Zulip is great, people are helpful, but it's not scalable. If you want to have hundreds of thousands of people using formal mathematics, Zulip will not scale. It would be amazing AI helping people to learn to use these systems, right? AI that suggests the next step when you are blocked, AI that tells you, why don't you try to do that? Have you seen these results? I think these 5 theorems that people proved before are very useful for you. We won't block you. Having AI that can do that, I think this is in reach and something that will help a lot the mathematicians using it.
Okay, maybe that's a good place to stop. So we're gonna go continue to lunch, if anybody wants to join.